All right, some more advanced topics. Perhaps the most powerful one is versioning and time traveling. So in TileDB, every write is immutable. Remember, every write creates a fragment, a timestamped fragment that will never change. It's immutable, and that's why it's awesome for object stores, because in object stores, every object is immutable. So this aligns very, very well. Again, it's timestamped, and this allows TileDB to do the versioning. Effectively, this is every separate write creates some kind of versioning, and you can move around. You can see views of the array as if some of the writes never happened. So I'll give you some examples. Suppose that this is what we write in the beginning. That's a fragment, a T1. Then we write something else. You can, in dense arrays, you can write portions of the array. TileDB is not going to write anything for this. So it's smart enough to understand, okay, this is only one portion, and I'm going to minimize the amount of data we write for this. Then you can read a timestamp 1 effectively from the beginning of time till timestamp 1, and this is what you're going to see. Or you can read between 0 and now, or timestamp 2, and you can get the updated version. Or you can read after T1 and up until T2, and this is what you're going to get. So superb flexibility here. And the sparse case is the same. It's exactly the same thing. I do a write here, I do a write here, and depending on the time range, I slice different things. The one thing that I want to mention for sparse arrays is that if sparse arrays allow duplicates, and this is specified in the schema, you can see it in the docs, then in this particular case where this write happened and this 40 effectively existed before. So if you don't have duplicates, you're not going to get the previous value. If you have duplicates, you're going to get it. And this, again, for certain applications, is very important to get the duplicates. All right. So I'm going to show you something real quick. Let's see. Dense versioning, for example. So we create the same array again. We write the array. I will get this write info over here. It's an auxiliary function to get the timestamp of this write. I am able to get the timestamp of each write and record it. So I'm just recording this. Then this creates one fragment over here, no problem. Then, and this is how the write info looks like. I can get the fragment name and the timestamp. And then I can open it and read it, no surprises. Then I will prepare some more data and just update this array. I'm going to write again. I'm not going to update. I'm just going to perform another write. So this is going to create another fragment. You see now 2 fragments. And I can read it. I can see that this took effect. And now I can time travel. And I time travel by passing a timestamp range over here in the open function. So here I'm saying, okay, I want between 0 and T1. So I get the original. This is the original data. Or I get after T1, and T2, and this is what I get. And you see these values are just empty special field values. They mean I have nothing there. It's not 0, I have nothing there. Okay, so very powerful to time travel. And actually we have more functionality than this, but this is sufficient for this, for the purposes of this webinar. All right, now in terms of indexing, I have covered a lot around fragments and a lot around dense and sparse arrays. But why is TileDB fast? Because TileDB is more than just a format, right? It's a format, but also an engine that makes slicing very, very fast. So here's how we do it. TileDB has a 3-level kind of indexing approach, if you think about it. The very first one is on the fragment timestamps. So if you time travel, just by the names of the fragments, we can discard. We can say this is not relevant because it doesn't fall in my range. The second is the non-empty domain in each fragment's metadata. Like there is a file, fragment metadata, inside each fragment, and it has the non-empty domain so that we know whether a slice is relevant to this fragment or vice versa. And finally, depending on whether you have dense or sparse, we may use some offset arithmetic for the dense case, and I'm going to show you this, or we use R trees in order to discard tiles. So with the very first 2, we're discarding fragments completely. Don't read the fragments whatsoever. With the last one, we are discarding tiles. And that's why we do the tiling. We do the tiling so that we help indexing, or we can build indexing on top so that we help TileDB discard tiles or disqualify tiles that it doesn't need for the particular query. So the algorithm looks like this, just a pseudocode. I get the list of fragments. So perform a list request, right? Get the fragment names. Then ignore fragments that are not in the timestamp that you're looking for. Then ignore the fragments whose non-empty domain doesn't intersect with your query, and then do the rest of the indexing magic on tiles, which I'm going to explain here. So suppose that this is a dense array and it has a 2x2 space tiling. So if I'm asking for this range, I don't need extra indexing. I know that this is dense. I know that these are fixed sized and populated. I know in a dense case that these are going to be populated. I know the order of the tiles. So this one is going to go first, and this is going to go second, this third, and this fourth. So when I slice here, I know that this is the second, and this is the fourth tile from the disk. And I know the offsets. The offsets I keep in the fragment metadata. I keep the offset of each tile so that I can go and grab it. But I don't need an extra index for this. But for the sparse case, remember, there is the global order and the capacity, and those dictate the shape of these minimum bounding boxes of each of the tiles. They look like this. And again, the order is going to shape the tiles differently, but they're going to look something like this, right? So what we do is that we take these MBRs, we put them at the bottom level of a structure, and then hierarchically we group, and that's how we create an R tree. That's an R tree, a bulk loaded R tree. And we just need a top-down traversal in order to slice efficiently and locate which minimum bounding rectangles intersect with my query, because those are candidates for results. We still need to grab them, open them, and check the coordinates to see whether they fall in the slice. And that's it. All right. One of the last topics is consolidation and vacuuming. Super important, super powerful. This merits a separate webinar, which we will do. But I want to give you some ideas here. So the important takeaway is that if you keep on writing to the array, and if you write very small fragments, right, you're going to end up with numerous fragments. And this is going to lead to performance degradation, okay? Because you may lose the locality of the data, and also the listing requests, for example, on S3 are expensive, and they cap the number of objects they return, like 1,000. If you have 1 million, you need 1,000 requests, and those requests are serial. So listing is expensive on cloud object storage. They're not expensive on your local storage. So you can't afford to have millions of those. So TileDB supports two levels of consolidation. The first is the fragment metadata, and I'll tell you why. And the second is the fragments. So the fragments are straightforward. You're just merging fragments together in the hope to vacuum the consolidated ones and come up with fewer. But the fragment metadata is a much cheaper approach for consolidation, which just consolidates very small information for all the fragments in one file. And you can locate, for example, the non-empty domains. So one level of indexing gathered in a single file so that you ignore fragments very, very quickly. So this is quite powerful and very cheap to do. And all fragments are preserved after you consolidate, because you can time travel. You can still have fine granularity for time traveling. We keep them. But if you want to discard them, you can. Right? There is a vacuuming process and you can do it. But time traveling is not going to work after you vacuum, right? Because that granularity for time traveling is lost. So that's it. I can show you very, very quickly something on this. All right, so let's say sparse consolidation. Here's what we do. Same array. We write once. We write twice. Just 2 writes. You can see the results. You can see the 2 fragments. What we can do is that we can consolidate the fragment metadata like here. We configure the mode for consolidation to be fragment metadata, and we just consolidate. That's it, very simple. And this is gonna create this file, this meta file. This gathers information about this fragment metadata and this fragment metadata, very small. And that helps avoid gathering the non-empty domain for every single fragment from those separate files. Like, it gathers it in one, and then this massively boosts performance, especially on S3. Okay, same data here. If you want fragments, this is the default, by the way. You can just ignore this or set the consolidation mode to fragments. And what this is going to do is create yet another fragment. That's what it does. And the previous ones are preserved. The data is still here. Nothing, no surprises. Time traveling works. You see, this is the original data. So it works. But then you can vacuum the fragments by just invoking this command. This is going to delete the two fragments that got consolidated into this. And the data is still here, but you cannot time travel. And that's it. So I'd like to show you one of the most exciting features that made it into TileDB in 2.3. However, we never announced it, we never showed anything. So I'm going to show you something really cool today. And this is called attribute filter pushdown. So up until now, I told you that TileDB slices very fast. That's fine because it has the index on the dimension, so it slices very fast. But what if I want an extra condition on an attribute? Ordinarily, what you would do is you would slice from TileDB into pandas, and then you would continue with pandas. I'm talking about Python. Like, of course, you can do the same thing in R and other languages, and of course in SQL as well. But what if we pushed that attribute condition down to the engine so that we filter inside the engine before we give you the results? Because just giving you the results may take a lot of time. If it's like billions of records and you just need a portion of it filtered by the attribute, then we're copying a lot of stuff. Even internally, I'm not talking about copying into pandas. We adopt zero copy techniques there, but still we're generating a lot of data for the result buffers, the buffers that will hold the results, right? So can we avoid this? So TileDB supports this attribute filter pushdown. It significantly boosts performance. Much fewer data gets copied around. It's more L1 cache conscious, and we can take advantage of vectorization and parallelism. So these are internal stuff, but it helps us. Like if the user gives us hints on those filters, we can compute them very, very fast internally. So I do want to show you this. This is it. So here's what I did. Okay, I'll post this this tutorial. You can ignore this. This is something internal for optimization of the results, of the result buffers, so that because I'm going to query a lot of data in this particular example. So I downloaded the NYC taxi data only January of 2020. It was 560 megabytes. I ingested it with this command. You can see it documented on the API reference. I made it as a two-dimensional sparse array. These are the index columns. I passed some filters and whatnot. It took 16 seconds to ingest locally on my machine. I have 8 cores. This is the array schema, like a lot of attributes here. And the total space is 105 megabytes with Z standard. So you can see columnar format and whatnot, like TileDB is very good at that. And then I can read it. I can query the whole thing. So this is what I'm doing. I'm querying the whole thing. It's like 6 million records or something like that. And I'm performing an extra attribute filter here with pandas. And this takes like 4 seconds. It varies if you run it multiple times, it varies, but that's what it is. The total result is 1.6, from 6 million down to 1.6 million. Okay, that's what I did here. Now, I can push this condition. It's the same condition, right? It's the same condition, but I'm pushing it down inside the query. So I'm creating this query condition object and I'm passing it into the query. And I don't need to do any filtering in pandas. I'm just going to store the data in pandas. And the query goes down to 1.3. So massive performance difference. Actually, one here, 2.2 versus 3.9. And then I can do also end conditions. I'm sorry. We support only end conditions for now on different attributes, same attribute doesn't matter, but very soon it's going to be more, and it's going to be more complicated expressions. This is just to make a point that the technology has been built, and now it's a matter of supporting more conditions down into TileDB. But this provides a significant boost, and we will try to do even more, like push down group bys, joins, and so on and so forth, but primitives at this stage. And the last super exciting feature that shipped with 2.4, like today, is this schema evolution feature that a lot of people have been asking for. So it's ready, and I'm going to demonstrate it. So this allows us to alter the schema. And for now, we can only add or drop an attribute. But in the future, imagine that anything will be changed, can be changed, like the capacity, the tiling, everything, right? And this is versioned. That's why it took us that long. It's versioned. You can time travel. You can do everything you want as you did with the rest of the stuff that I showed you, but now on a different schema. More features are coming up, full version time traveling supported. So let me quickly show this to you. Let's do this. So same array as before, one attribute in the beginning. We write some data to it, right? This is the schema created. Remember from creation of the array. This is how the data looks like. And this is what I slice. I'm sorry, this is version. I want schema evolution. I apologize. Up until there, it's exactly the same. It's exactly the same. And here's what I want to do. I want to change. I want to create a new attribute, and I want to add it to the schema. So before I had only A. This is what I had before. And I'm adding one attribute, which is int 8. Doesn't matter what it is. So if I print the schema now, I can see both those attributes. And if I slice the array, I get some fill values here because A2 did not exist in the write that I performed before. But still, now I see it, and I get some fill values back, which is the correct behavior here. And if I check out the contents of the array, you can see I have two files for the schema now, both timestamped, right? Because I changed the schema. I can perform another write to this array, and then I can slice it, and I can see that this write took effect. And for the newly written values, I provided two vectors, right? One for the first attribute and one for the second attribute. And this worked perfectly. And I can drop an attribute. So I can drop the first attribute now if I want to. So very simple. Schema evolution object, drop the attribute, and then evolve the array. So the schema has evolved. I see now only the second attribute. I don't see the first. And then if I slice it, I only see the first attribute, the second attribute. And that's it. So this is how schema evolution works very, very easily. And we're hoping to put more features into this feature. But this works today with 2.4. All right, guys, I'm done with the examples. I'm just going to touch upon a little bit on writing, a little bit on reading, and the work in progress and competitors, and then we will be done. So notes on writing, lots of flexibility with orders. Like if you use low-level languages like C++, you can boost the performance of ingestion. That's what we do in many, many applications. Everything works in parallel in a log-free manner. You can have multiple workers writing to the same array. There are going to be no conflicts, no consistency issues. We do not support deletions and updates just yet, but these are going to appear in very soon in later releases. Some tips for performance: the tile should be big enough. I don't know, 100 kilobytes to 1 megabyte. It depends on the application. It requires a little bit of tuning. Don't make it too small. Compression is not going to work. Don't make it too big. When you slice, you're going to bring too much information. So there is a trade-off. Each fragment should be about 1 to 2 gigabytes. So consolidate. And again, I'm going to have a different webinar for consolidation. Fragments should not interleave. So the non-empty domains should be kind of disjoint so that indexing kicks in. And do run fragment metadata consolidation often, because that's going to boost the performance on S3 a lot. Like without having to do too much fragment consolidation, just the fragment metadata consolidation is going to work well. Some notes on reading: TileDB is eventually consistent. This means that you can have reads and writes together, no problem at all log-free. But when you perform a read, you open the array and you see only committed fragments with the .ok file appearing there. It's not going to see anything else. And the read is not going to be affected if another write commits. It's just not going to see that write. But if you redo the read later, you are going to see that write. So this means that it is eventually consistent, right? Because S3 as well, at the time of the creation of TileDB, was eventually consistent. Now it is introducing more stronger consistency, but we want for now to tell people it is eventually consistent because we're log-free. This gives you a lot of flexibility when writing and reading in parallel. We do support reads in different layouts. Again, if you are more low-level kind of programmer and you want performance, TileDB gives you different layouts to optimize performance. We support streaming reads. This is super difficult to pull off. The reason being that in the dense case, you know what to expect. Like you know that, okay, I'm expecting 1,000 cells. So I can allocate my buffers appropriately. But if you have variable length attributes and if you have sparse arrays, this is difficult. How much are you going to allocate if you don't know how big the result is? So we have this feature, I'm not covering it here, but you can do stream reads. Things are not going to fall apart. Some tips for performance: allocate sufficient space for your buffers, like what I did in one of the examples I showed you. Again, different webinars for that, for optimization and performance. Tune the read and layout based on your reads. So try to imagine, what am I reading? How do I slice? Is it a square-like slicing, rectangular slice? What is it? So you can tune the layout upon array creation based on your reads. And push down slicing and attribute filtering as much as you can, because this is what TileDB is extremely good at.